All right, we're in Unit 1. We're talking about chapters 1 through roughly like 3, 4, and 5, and about graphical displays and how to interpret the data and how to graphically display the data, and some nice terminology as well. But our next topic here we're focusing in on is outliers, right? And this is to show you with data, like it looks like there's a large grouping of data here, right? And then you got this little thing out here. That is an outlier of your data, right? And extreme values are often called outliers and are found in many distributions, and sometimes they are the result of errors and measures of, just kind of happen randomly, and they do deserve some scrutiny. However, outliers can also be the result of something naturally happening, so you can't just discredit all of them because you see an outlier. Outliers may occur on one side. They could occur on both sides of data of your distribution. They can kind of occur everywhere. So your tip is this. It's a very simple tip. Pay attention to the outliers. You can't just say, it doesn't matter for my data set. That's not what happens with outlier. There is a formal mathematical definition for an outlier, which we will eventually get to, as a value at least a certain distance away from the first quartile and the third quartile, which is what these are. We will eventually get to those. First quartile, third quartile. All right, and you can definitively see if something is an outlier. Oftentimes people see a data out there, way far out there or way far out here, and they instantly look at it and say, well, that's an outlier. It might not be an outlier. It might be far out there, but it might not be an outlier. And we will learn how to calculate this distance later. Another tip, some distributions have many little ups and downs, which should not be confused with modes. All right, just because they have a couple modes, every little bump doesn't make it a mode. That one graph I showed you before, which had a big hump, it was for the Hodgkin's lymphoma. That was bimodal because each hump is a mode. Two of them bimodal. Those are definitely large, big, large lumps or humps that were there in the graph, right? Just having a whole bunch of little stuff doesn't make it a mode. So what are modes then, right? Well, some distributions have one or more, right? A normal distribution has one big, it's modal, right? It's normal. Those are called modes. The values with the peaks above them are the modes, and with exactly one or two such peaks, the distribution is either unimodal with one peak and bimodal with two peaks, right? But every little bump in the data is not a mode. You should always look at the big picture and decide whether two or more phenomena are affecting the histogram. Take a look at this example. The histogram I'm going to show you shows employee computer usage, number accessing the internet at given times of the company's main office. All right, so here you go. The question is that an outlier or not? All right, and we're trying to look to see, well, it looks to me like this is right here, probably one of the modes, right around here between 10 and 11 a.m., and this is probably another one in between 2 and 3 p.m. more than likely is when the access to the internet, right, the usage is at its peak. This is looking like it's bimodal to me. All right, computer usage at this company appears heaviest at the mid-morning and the mid-afternoon, with a dip of usage during the noon lunch hour. Okay, there is an evening outlier way out there indicating employees returning after dinner for perhaps custodial cleanup crews, taking internet breaks. There's a little blip on it out there. Doesn't make it a complete another outlier. It's just there's usage there way out there. And take a look at the shape of the graph. Distributions come in endless varieties of shapes. However, certain common patterns are worth special mention. 1. A symmetric distribution is one in which two halves are literally mirror images on each side, right? Mirror images. For example, the weights of all people in some organization fall into symmetric distributions with two mirror image bumps. One for men's weights and one for women's weights. All right, take a look at this. This is symmetric. I know it kind of looks funny, but right down the middle, if I fold one side over the other, it's still symmetric. Skewed right, all right, is a distribution that has its spread thin towards the higher area, or the right side. Skewed right. All right. For example, ages of people in their 90s have a sharp decreasing number as they move from 90 to 99, right? Skewed right, thinner to the right. Skewed left is a distribution that has its spread thin towards the lower end, all right, or the left end has thin values. For example, scores on an easy exam show a distribution this way, right? If it's an easy multiple choice test, most kids, the scores are up here more. It's skewed left, skewed left. The skew is talking about the lower end, basically. Bell-shaped. That is the symmetric distribution with a center mound, the biggest, and two sloped tails, right? Center right in the middle. For example, the distribution of IQ scores across the general population is roughly symmetric, right? The center, around 100. Most people are average. You have some people who are not so smart and others that are very smart, but it is, for the most part, bell-shaped. And uniformed distribution is a graph. It's just a horizontal line. For example, tossing a fair die and noting how many spots appear on the top yields. Just a straight line, all right, with a 1 through 6 because they all have the same odds, same probability of hitting. So it's just a uniformal one. Tips. When describing a distribution, always comment on the shape, outlier, center, and spread. They want you to comment on all aspects. When it says describe the distribution, this is huge for your AP exam. When they ask you to describe it, that's what they want. So they want you to refer to your socks, basically, is what I'm saying. Refer to your socks. You got your shape and your spread, and you got your outlier and your center. They want to know where all that stuff is happening. So when they say describe the distribution, refer to your socks. Okay? The shape, outlier, center, and spread. All right? In the real world, distributions are rarely perfectly bell-shaped or perfectly uniform, so we say roughly or approximately symmetric, approximately bell-shaped, or approximately uniform. You are going to use that word approximately a bunch on this exam. Okay? A bunch. All right? Approximately or roughly. Got to use it. It's going to help out a ton. Cumulative relative frequency plots. Sometimes, again, we sum up the frequencies and show the results visually in a cumulative frequency plot. All right. Some call this an ogive. All right, and take a look at one. The following graph shows 2017 school enrollment in the U.S. by age. Here you go. This is cumulative, a cumulative frequency, right? So taking a look at that cumulative frequency there over time, what can we learn from this cumulative frequency? All right, the cumulative frequency. It starts off growing and then it just doesn't grow as much over time, right? Is what it's looking like. We're trying to figure out the data. Now, this is the percents. Cumulative frequencies, right? These are the percents. Okay, so don't think too hard. These are the percents. So, for example, going up to the graph from age 5, we see that we get 15% of the school enrollment is below that. So what do I mean? Take a look. Age 5. That's 15%. 15% of school enrollment is below age 5. Check. Going over to the graph at 50% on the vertical axis, we see that 50% of the school enrollment is below 50% right here. Here's 50, right? Right there. Age, looks like 11, right? So over 50% of, well, not over, exactly 50%, all right, is at 11. That's the middle, all right? That's the middle ages of people who are enrolled in the U.S. in schools. Going up from age 30, we see, there's age 30, and that's at 95%, which means 5% is above age 30 that are still enrolled in school, which is not very many. Going over from 0.25 and 0.27 on the vertical axis, we see that the middle 50% of the school enrollment is between ages 6 and 7. So 0.25 This is roughly there, which looks like 7.27, right? Looks like it's between there and there, right? Between ages 6 and 7, all right, is where that will occur. Going over 0.25 and 0.27 on the vertical axis, we see that the middle 50% of the school enrollment is between ages 6 and 7. All right. A distribution skewed to the left, right, skewed to the left, thinner this way, has a cumulative frequency plot that rises slowly, all right, at first and then steeply later. So it rises slowly first, all right, and then steeply later. Distribution skewed to the right has a cumulative frequency plot that rises steeply at first and then slower later. Take a look at these pictures and consider the essay grading policies of 3 teachers. Abrams gives very high scores. Brown gives equal numbers of low and high scores. Connor gives very low scores. Histograms of the grades with 1 the highest score and 4 the lowest scores are as follows. So, 1 the highest, 4 the lowest. Okay? And 4 the lowest. So, low scores as skewed to the right, as skewed to the left, and that's normal, right? These translate into the following cumulative frequency plots. All right, these translate into these. Again, taking a look at them. Right smack dab in the middle was brown, normal curve. And notice it just kind of normally right in between. And then we said this one has a majority of the scores at the higher end and lower down there, skewed to the left. Skewed to the right. Thinner at the right, skewed to the right. And if it's skewed to the right, notice if it's skewed to the right, it jumps up right away. And if it is skewed to the left, right, it's slower and then steep. Right? So the idea was just to show you how they compare to one another. Right? Abraham is skewed right. So if it's skewed right, all right, distribution skewed to the right, rises steeply to start. That's what we said. Rises steeply to start. And that's exactly what happened. Abrams is rising fast and then slows down. Connors is skewed left, which means it doesn't really rise right away, but then it takes off more towards the lower end of the scores. And that's exactly what happens. Connors is slow and then starts to speed up. And then Brown's is symmetric, all right? And because it's symmetric, right, it kind of goes up nice and slow and kind of comes down nice and slow, nice and even the whole way. So, take a look at this summary. There are 3 keys to describing a distribution or shape: center and spread. All right. Summary: don't forget about the clusters, gaps, modes, and outliers, and always provide context in everything that we're doing. Look for reasons behind any unusual features that you see, and remember the shapes of graphs like skewed left, skewed right, bell-shaped, uniformed, all that. We have categorical or qualitative data. It uses dot plots and bar charts. They're useful, right? Categorical qualitative, right? Data uses dot plots and bar charts mostly. Quantitative normally goes with histograms, cumulative frequency plots, stem and leaf plots, right? Those are normally quantitative. In histograms, relative areas correspond to relative frequencies, right? Relative areas, relative frequencies, percentages, right? So with that in mind, we can wrap this all up. And that is kind of Unit 1, chapters probably roughly 1 through 4 to 5-ish.